Hi everybody out there, this is Obi-Wan Pez for N Simplex Pachinko. Tonight is yet another math night, so if anybody is out there and wants to have any questions answered about mathematics, about any particular topic, feel free to drop in and let me know. So for tonight, what I had in mind was to look at why this channel is particularly called N Simplex Pachinko. There's a little bit of history behind it, and I mean, as always, and I figured I would look into my notes talk a little bit about again, the history behind the pictures that were on the splash screen beforehand, and talk a little bit about all the rest of that. So anyway, the idea behind N Simplex came up a while back. A friend of mine saw me working on some research and said, "What are you working on?" And I told him precisely what I was working on. Our institution was at the time starting to get interested in doing some more research at the two-year college level. Most of the time it doesn't really happen, or there's very little research being done at the two-year level, just because students come and go so quickly. By the time that they're done with most of their major courses, they don't really have time to do research, or they're not sticking around for long enough. So a lot of our students are just kind of quick in and out. However, the last few years we've had several students who stuck around for 3-4 years, give or take, leisurely racking up their credits, getting their two-year degrees, or they've been sticking around for 2 years, but they were already at or above the Calculus 2 level and got really serious into trying to do some mathematical problems. So a group of them had decided that they were going to look at what is known as Pascal's triangle. If you are not from one of the European countries, this may have a different name for you. So, do keep in mind that, unfortunately, our, mathematical intelligentsia have been very Eurocentric for about the last 500 years. So, in and around let me back up. There are really 3 parts to Pascal's triangle when we're looking at it from a historical perspective, and maybe wanting to give credit where credit is due. The first one, actually, that I would say would be number theory. And in number theory, what someone had done was said, okay, well, let's take a field of hexagons. That's not a hexagon. So if we just have like a field of hexagons that are going on forever and ever in every direction, and at some point you just kind of arbitrarily start with a 1 somewhere. and all the rest of the surrounding and above hexagons are all going to be zeros. What we want to do is look at the next row, and on the next row, the number that will be entered into each of these hexagons is the sum of the two numbers directly above it. So in this particular case here, we've got a 0 to one side and a 1 to the other. 0 plus 1 is 1. On the other side here, we've got a 1 plus a 0, again, 1. On the outside of this, we only have zeros that are going to be off in every direction forever and ever, so these are going to be zeros on the edges. And we can continue this downward. So, you know, these are all still, again, going to be zeros. Anything above the first one will also be a 0. And that's just going to keep going. Again, down in this direction, off in that direction. They're all going to be zeros. Coming down, however, we have here now a 0 and a 1 gets us a 1. 0 and a 1 gets us a 1. So this diagonal is just going to keep being 1s. It's still more interesting than zeros. And on the outside, the diagonal over here will also be 1s. Again, we're going to have a 0 out there, so it keeps going. All right, now the slight surprise comes in. It's not really a surprise, but slight surprise comes in this middle space here where we have a 1 and a 1 combining here to make 2. And on each of these places we have a 1 and a 2, which makes a 3, and a 3 again. On the next row, we also then have a 1, 4, 6, 4, 1. When you add all those up into the proper locations, we then have a 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and this continues. We can go as far as we want with this, but the idea here is that still our outside numbers here are going to be 1s. As we come in to the middle here, we start adding up these numbers, and again we start getting 1, 2, 3, 4, 5, 6 right along that second diagonal. Along the third diagonal, this is going to be slightly less obvious, but add 1, add 2, add 3, add 4, add 5, and add 3, add 6, add 10, and add 15 for the next one. So essentially, we're just taking the numbers along the diagonal and we're adding the opposite number, which is coming down from the other side. So the first known usage of any of this came from the binomial coefficients area, which I wouldn't have thought would be the most obvious, but that was the case. So in the binomial coefficients area, we had a mathematician known as Pingala, and he was around 2nd century BCE. So roughly 2200 years ago was the first known instance of this pattern being used. Now it wasn't set up into a triangle exactly, however, shortly after his time, no. All right, after his time, it was set up into a staircase pattern. Oops. Right around 755 CE, the staircase of Mount Meru became the manuscript that highlighted the shape of this triangular sort of pattern that we had here. All right, so sometime after that, this pattern moved a bit to the... Okay, cool. Didn't cut myself off. This pattern moved a bit to the west, and a poet, mathematician, and astronomer named Omar Khayyam ended up working on the same problem. Make sure it's spelled right. And this was around 1060 to 1100 CE. Don't know exactly when it was, but somewhere in that neighborhood. So again, this is a really old problem. So those people in Iran, at least many still today, may refer to this as Khayyam's triangle. It was actually invented by the Persian mathematician Al-Karaji, which was roughly 100 years before Omar Khayyam, but unfortunately the manuscript was lost and has not been recovered. So we don't have technical proof, although there's some reference to it. So somewhere in the 980 to 1020 CE area. I'm off the map, aren't I? Yeah. All right. Let's move all that. Cool. Alright, so again, India, Persia, all these places had this pattern like well before any of the European nations. Alright, so in number theory, the first person to really come up with, again, what we know as Pascal's triangle was a Chinese mathematician named Yang Hui, who again came up with this around and about the 1260 to like 1290 range. And the actual manuscript was written in 1303. Terribly messy today. Okay. The triangle itself, again, for more of the sorry, gotta check the notes. Okay, well, as it turns out, the number theoretic Pascal's triangle also dates further back than Yang Hui. It is also known as Yang Hui's triangle in China. Dates back to Jiaxian in at about 1050. And Yang Hui was really the first one who presented it and made it a little bit more public knowledge, and that's why his name gets attached to it today. So Jiaxian ended up doing some of the first instances of it, but again. And even prior to Pascal getting his hands on it, there were other Europeans who also knew about all of this, these other triangles, or the triangle, through its many different uses. So it appears for the first time in Arithmetic of Jordanus de Nemore in the 13th century. So 1200s. It ends up being binomial coefficients, end up being calculated by Gersonides in the 14th century using a multiplicative formula, which is again more or less what Yang Hui did. And Petrus Appianus also published the full triangle in the 1500s. So again, Pascal really did not do any of this stuff here, the binomial coefficients or the number theory. Pascal's main work with this particular triangle has to do with probability theory. And what are known as binomial distributions. Okay, so doing binomial distributions was really Pascal's thing. He ended up publishing this in 1655. In a French traité du triangle arithmétique, or I'm sorry, treatise on arithmetical triangle. So the arithmetical triangle being the additive terms that you can go down. He, touched on some of the other stuff, the number theory, the binomial coefficients, but really wanted to focus on probability theory because that was the new thing that he was coming up with. So in most Europeans' minds, he ends up getting the credit for just the triangle because he was really the big, he was the one who came up with the, biggest seller here. It wasn't actually named Pascal's triangle until Abraham de Moivre named it in 1730. So again, he was really the Abraham de Moivre was really the first one who named it Pascal's triangle. Pascal was not that much, didn't have that huge of an ego. Also, the influence of the triangle itself probably, started in India, and the Chinese became interested in mathematics and sent some of their people over to India. At some point, there was probably some crossover. Similarly, the Persians also sent some of their people out into India and Greece and all over to try to collect as much knowledge as they could. So it was very likely that the Persians also picked up their structure to the triangle from the Indians directly. In Europe, this also could have been, again, another instance where they ended up collecting their information from the Persians or at the appropriate time. Yeah, I don't know my Middle East history all that well, sorry. But at any rate, we also have, so we have the probability theory. Right, so we have the three main areas where this triangle comes in. Again, number theory, binomial coefficients, and probability theory. Now, realistically, these are all related to each other anyway. They're all pretty much the same thing. What happens later on is that we end up with multiple ways of coming up with these numbers. So the first was, again, just using number theory. So start with a 1 and a field of zeros, and then as you go down in these hexagons, or the Chinese just had lines drawn, which formed hexagons, but it just kind of went out, actually as a diamond pattern. In terms of the binomial coefficients, what you can get here I promise I will bring this back to why my channel is named after this, but we'll get there. So there's a lot of background. The binomial coefficients, what you do is you look at an algebraic term, a plus b, raised to the nth power. And what we care about, again, are the coefficients. We don't really care about the individual terms or what they're named or whatever we've got. We're just really focusing on what are the coefficients of these terms, a and b, as we go through a power, a plus b raised to the n. So in the case of n equals 0, this one's nice and easy. A plus b raised to the 0 power is just going to be 1. All right, with n equals 1, we end up with a plus b raised to the first power. So we're going to have 1a and 1b. In the case of n equals 2, most of you probably don't need to do this out. You could probably do it in your heads, but we start looking at a plus b squared is a plus b times a plus b, which is a squared plus ab plus ba plus b squared. And again, we don't actually need to worry about AB and BA. They're the same thing by multiplicative commutation. So commutative property of multiplication, you are allowed to multiply two numbers in any order you want. The result ends up being the same. So here we have an a squared. We have 1, 2 ABs, and we have a b squared. So a squared plus 2ab plus b squared is going to be 1, 2, 1. N equals 3, we end up doing the same thing here. So this is going to be, you know what, let's just take this one. So a plus b squared is a squared plus 2ab plus b squared, and then we multiply by another a plus b. You multiply everything by a first if you want, and then multiply everything by b second if you want. Another option is to take a plus b and give it to each individual term. So it doesn't matter to me how you do it. It's more or less going to be the same. So this is going to be a cubed plus 2a squared b plus a b squared plus a squared b plus 2a b squared plus b cubed. And again, here for multiplicative commutation, or in this case we don't actually have that, but look for the terms that are the same: ab squared, a squared b, a squared b. These are like units, so you can't add feet and inches together unless they become the same thing first. In this particular case, a squared b and ab squared just are fundamentally two different units, so you can't add them together. So a cubed plus, okay, last line. Here we have 2a squared b plus 1 more makes us have 3a squared b plus 1a squared b plus 2 more is going to be 3ab squared plus b cubed. And so here we have 4 terms. Their coefficients are 1, 3, 3, and 1. Now at this point you might be able to just trust me. Otherwise, I recommend doing this out manually at some point, just to check, make sure you got an understanding of how this works. We get our 14641, and again here we have a symmetric property between the two sides, because on the left hand side, left hand for you, on the left hand side we have these terms which are counting down. So we have 3 A's, 2 A's, 1 A, and no A's. And we also have no B's, 1 B, 2 B's, and 3 B's. These are counting up as they're going to the right. And the symmetry occurs because at the beginning we had one of each, 1A, 1B, and when we raise those to a power, we're just multiplying stuff over and over and over again. So again, we end up with the same stuff on both sides. N equals 5, 1, 5, 10, 10, 5, 1, and it exactly matches the triangle Khayyam, Pingala, Hui, Xian, and Pascal, and even a couple of other people that came before. I'll probably find them out later. That's not helpful because it went right off the screen. Cool. All right. Nope. All right. So again, these binomial coefficients, a plus b raised to the nth power, ends up getting us the Pascal triangle just in the same way. Or rather, the Pingala triangle, staircase of Mount Meru, if we want to go back to earliest. Okay. So, based on all of this stuff, this is the sort of thing that we're working off of when we get to Pascal finally. So Pascal then says, well, what if A and B represent two probabilities? Like, for instance, the probability of throwing a coin up into the air and getting a certain number of heads and a certain number of tails. Well, if it's a fair coin, then this is going to be a probability of 0.5 for h plus 0.5 for t raised to the nth power for n flips. So you have n flips of a fair coin. You're going to end up getting these coefficients for these probabilities. So for the first one, if you don't flip the coin at all, then there is a perfect 1 probability that you will get nothing. Right? That neither heads nor tails will be flipped. In the case of 1 flip, then we have a 1 times 0.5h plus 1 times not point times 0.5 t. And again, this makes perfect sense. We're going to have a 50-50 probability. 1 will land on heads, 1 will land on tails. If you just flip the coin once, 1 head is a 50% probability, 1 tail is a 50% probability. So fair possibilities here. If we go with 2 flips, this is n equals 1. If we do n equals 2, we got 2 flips, so you flip it up in the air twice. You're going to get a 1 times 0.5h parentheses squared. Oops. So there's a 1/2 probability twice over that you're going to get heads twice. All right, plus 2 0.5h times 0.5t plus 1 times 0.5 t squared, or t parentheses squared. So in this particular case, 0.5 is 1/2. When you square a half, you get 1/4. So you have 1/4 chance that you are going to land with 2 heads, plus a half times a half is again 1/4, but we're multiplying by 2, so that's 2/4 or 1/2 again. There's a 1/2 probability that you will land 1 head and 1 tail. I'm sorry, I don't know what's going on with my pen here. It's kind of making tails and going all over the place. All right, plus, here again, 1/2 squared ends up being 1/4 t squared. And now if you add up all the probabilities, the probability that any of these in total could happen is 1/4 plus 1/4 is 1/2 plus another 1/2 is 1. So this is working out. If you want to know what the probability of hitting 3 heads in 6 flips is, then you go down our chart here and you'd find n equals 6, and then you'd say, okay, 3 heads is when we have h cubed. This 1 here is what happens when we get 6 heads in a row. Not very likely. But if we get 5 heads, 4 heads, or 3 heads, there we go. So this one here is going to be 20. Or it will likely have 20 flips out of the total for the entire row. So then this is 1, 6 is 7. 7 on this side is 14. 15 and 15 is 30. So 14 and 30 is going to be 44, plus 20 more is going to be 64. So the probability of getting 3 heads in 6 flips is going to be 20 over 64. We can divide both by 4. We get 5 over 16, 5/16. Now I'm only able to do that. I cheated a little. I'm only able to do that because this is a fair coin. If you want to see the math out further, we're going to have to move on to the next page. So we want the term that we had here. So this is 20. Times, and maybe you'll be able to fit it in. So this is going to be our 1/2 h times our 1/2 t, and each of them raised to the necessary power. Again, we said we wanted 3 flips out of the 6. So 3 of them need to be heads, then the other 3 are going to be tails. Okay, so what we have here now is a 1/2 cubed times a 1/2 cubed. Well, a 1/2 cubed is 1/8 times 1/8 times 20 from the coefficient, and 1/8 times 1/8 is 1/64. It's going to be 20/64. All right, so what if it's an unfair coin? Again, I'm getting a bit far afield, but if it lands 60% heads, 40% tails, so not really noticeable necessarily on any one flip, but over time you should be able to notice that this is not going to work properly. Start skewing a little bit more towards heads. Now in the same row we had 1, 6, 15, 20, 15, 6, 1 for n equals 6. All right, now what's the probability that we get 3 heads? Three heads of 6. So in this particular case, 3 heads out of the 6 flips, we're going to end up with, again, the 20 for our coefficient, times the probability of the heads cubed, times the probability of the tails cubed. So what we've got for heads is 6 out of 10, or 3 out of 5. And tails is going to be 4 out of 10, or 2 out of 5. Okay, now what we need to do is to calculate the probability that each of these are going to be flipped. So 3/5 cubed is going to be 3 to the 3rd, or 27, over 5 cubed, which is 125. So 27 1/25. Tail side, this is going to be, and this is still times 20 out front. Tail side, 2/5 cubed is going to be 2 cubed over 5 cubed. Or this is going to be 8 over 125. Alright, so these are getting a little bit tedious, but it's okay. 20 and 125 will have a 5 in common, so we can divide out a 5 from this 125 and this 20, because these are being multiplied. 20 divided by 125. So here, if we divide out a 5, we end up getting a 25 in the denominator. And here, divide out a 5 from 20, and we get 4. There's no other common factors anywhere else in here. You could tell from the original numbers that we were using. So we've got 5s and only 5s in the denominator, and we've just cleared out the only 5s we had up top. Just the 1. So now we've got 4 times 8 is going to be 32 times 27 over 25 times 125. I mean, yes, I can probably do this in my head, but 625 times 5 is 3125. Yep. Cool. Someday I'll show you my rearranging multiplication. So 32 times 27, it's not actually that hard, but 864. Or if we wanted to do this in the Hindu Veda style, oops. I think I did this last time, right? So here you say, how do you get the ones column? Well, that's how you multiply the ones by the ones to get the ones. So that's going to be 2 times 7 is 14. Carry the 1 down bottom. How do you get the tens spot? This is ones times tens or tens times ones. So here we get a 3 times 7 is 21 plus 2 times 2 is 4. So 21 plus 4 is 25 plus 1 is 26. Carry the 2. And how do you get hundreds? That's tens times tens. So 3 times 6 is going to be 6 plus 2 is 8. So 864. This is nice and easy as long as you can keep a couple of numbers in your head and then add them together manually. It only takes you one extra line or one line in total to give the answer. And this was outlined in the Hindu Vedas thousands of years ago. So whenever the Vedas were written, there are pretty explicit instructions in order to get addition, subtraction, multiplication, and division. So all 4 of the basic operations. They also talk a little bit about some other math that's in there. It was important to their society, so they put it in their holy book. So 864 over 3125, you're not going to get any better than that in terms of fractional value, but if we get a decimal, this is about 27.65%. So the chances of 3 of your 6 flips, exactly 3, being heads, then you end up with this 27 out of 65. If you wanted to look at out of the 6 flips, let's say that your win condition was at least 3 were heads. So then you'd have to look at this in terms of, okay, well, we got the 3 here, 4, 5, or 6, and then we could add all of those up. So, we could go 1 times, and again here we have 3/5 h parentheses to the 6th plus 6 parentheses 3/5 h to the 5th times 2/5. That was a bad habit. Sorry. T to the 1st. Really, I should note, this also has a multiplied by 2/5 t to the 0, but this term is just equal to 1, so most of the time we ignore it. It's a bad habit. I don't recommend actually ignoring it. So just make your teachers happy, right? And write it out like that, and they'll know that you know what you're talking about. Okay, so 3/5 h to the 4th times 2/5 t to the 2nd plus our 20 that we found earlier. And we'll shortcut this because we already did it. 3/5 h to the third times 2/5 t to the third. Okay, so again, we ignore the other term because it's just equal to 1. And here we get 3/5 to the sixth. H to the sixth. Plus here, we're going to do the same thing here. This is going to be 6 times 3/5 to the fifth times h to the fifth times 2/5 times t plus 15, parentheses, this is going to be 3/5 to the fourth h to the fourth times 2/5 squared t squared plus, and now we have the other one that we already found. That was the 864 over 3125, and this was h cubed t cubed. Alright, so we can do all of this stuff. This is going to be 3 to the 6th power. Right, so 3 to the 4th is 81, times 9 again is going to be 721. Oops, 721 over 5 to the 6th, which we already know is 3125. Nope. Nope, nope, nope. Sorry, that's not 3125 because this was 1, 2, 3, 4, 5. So 3125 times 5 is 15,625. So 15,625. Apologies to any European/Canadian viewers who might realize that the American comma is actually, for some reason, the thing that doesn't mean anything in a number, whereas the tiny little decimal point is the most important thing to determine where the decimal place value is, whereas in most reasonable countries that's reversed, and the big obvious thing is the thing that matters, whereas the little tiny dots are the ones that don't. I'm trying to advocate for switching, but they don't listen to me. So. Okay, so we got here 3 to the 5th times 2 times 6 is 12. Or we could look at this and say, well, 6 has a 3 in it. We already know what 3 to the 6th is. It's 721. So the 3 from the 6 times the 3 to the 5th is 721. Times 2 is going to be 1442. Times the leftover 2 from the 6 is going to be 28. What did I say? 14,442. No, 14. Well, 1442. So 2884. Whew. Over 15,625. This is h to the 5th times t. Or t to the 1st if you prefer. Nope. Man, I messed that up. Okay, hang on. $729. That was my issue. Okay. Times 4 is going to be 2916. Okay. Okay, plus can do somewhat similar stuff here. So we got 3 to the 4th. We only got one other 3 there, so that's 3 to the 5th. Almost. Alright, so 3 to the 6th then. And it's going to be 729 over here. Let's not mess it up too bad. Okay, so let's go 3 to the 4th is 81 times 15 is 1215 times 2 squared is 4 is going to be 4860. Out of 15,625 is going to be h to the 4th t squared. Okay, plus, and let's actually unrationalize this for a second, or not rationalize, unsimplify it for a second. So it would actually be more convenient if we had it in the same terms. So if we multiply both top and bottom by 5 again, then we end up back more or less where we started here. So this number here, had I left it as it was, would have been 4,320 out of 15,625. And again, this is h to the 3rd, t to the 3rd. So on this entire line, we have what ends up being 15,625 flips represented. And of those 15,625, 4,320 would be represented with 3 heads. 4,860 would be represented by 4 heads. 2,916 would be represented by 5 heads. And 729 would be represented by 6 heads. So if we take all those numbers and add them together, this gives us the sum total of how many flips we would end up with, or the probability of the, okay, just the tops, would end up getting us the number of flips where we end up getting 3 or more heads. So 4320 plus 4860 plus 2916 plus 729 is going to be 12,825 divided by 15,625 total flips. 15,625 is a very nice 82.08%. That is exact. That's not rounded either. So on an unfair coin that is weighted 60% heads, 40% tails, you end up with 82% of all flips being 3 heads or more. If we wanted to like split it, never mind. We could split out the one in the middle and say like how many for just this, but that essentially just ends up, I mean, it just changes the numerator, so it's not that hard or anything, but 12,825 minus the 4,320 that we had over there was 8,505 divided by 15,625. So just for these over here, 4, 5, or 6 heads, you end up with a 54% chance. So better than half, and you're only talking about these 3 terms. And 4 that you're not including. Okay. So, how does all this relate to what I'm doing? There you go. All right, so a bunch of our students figured out interesting patterns that existed in Pascal's triangle. Young-Hui's triangle. Pangala's triangle. All right, going back. They said, okay, let's take this as what happens as we go across. So here we're going to have 1 to 1. You're just going to multiply by 1 to get over to the other side. Here, to get from 1 to 2, you multiply by 2. To get from 2 to 1, you multiply by half. All right, this should not be surprising. Again, it's going to end up being symmetric on both sides. We have this times 1 here. We have this times 1/3 here. We have it times 3 here. Again, times 4, times 5. You're just multiplying by those same numbers. However, when you get into this other area here, now we start getting somewhat weird stuff. Oops, 1/5, 1/2. 4 to 6 ends up being 3/2, and 2/3, and 1/4. So as we start going down the triangle, we see more and more of the fractions that are going to be represented are going to show up again and again and again as we keep going down further and further. And I believe if you look at the diagonals, yep, that was it. If you look at the diagonals of the multiples, then here we just have the integers. These here end up being all of the integers over 3, or over 2. So 1 over 2. 1 is 2 over 2. 3 over 2. 2 is 4 over 2. So this is all integers over 2. This is all integers divided by 1, essentially. Over here we have integers divided by 3. Here, integers over 4. And here, integers over 5. So these numerical representations just keep popping up all over the place. And, you know, these particular students delved into a little bit of some interesting, like, how did this happen, to kind of try to uncover some of the patterns that exist behind it. Another group behind them, I don't remember the exact stuff about this research, but like they basically picked any particular multiplier that's here and looked at the 6 numbers that were around it that were also the multipliers. So they said, like, okay, in this case 2, we've got a 4, a 3/2, a 5, a 1, whatever the next ones are going to be, 6 and 15, right? So that's going to be an interesting one. Times, let's see, the 6 is out of range. 6 to 15 is 15 over 6, or 5 over 3. Nope, 5 over 2. I promise I'm okay. 5 over 2, and then over here the next one, 4 over 3. So they looked at some interesting ideas. They called these flowers. So we looked at the flowers of all of the numbers that were directly, all of the multiples that were directly around any particular value. So you just pick one and then look at the patterns that exist in the rosette that's around it, essentially. So there were some interesting and cool ideas. Another group in that same year decided that, you know what, doing this on like Pascal's triangle is all good, but what if we did this in 3 dimensions? So they said, okay, if we did this in 3 dimensions, this gives us a picture that looks, roughly speaking, like this, where we have It's kind of like it's a three-dimensional representation. It's awful, but trying to like make this stuff closer, a little darker. So they said what would happen if we took the numbers that were in this tetrahedron and sliced off the face of each side of the tetrahedron. The three exposed faces that are going up and down are going to be themselves Pascal triangles. So the 1 and 1 at the front, the 1 2 1 at the front, the 1 3 3 1 on the next layer, and then over on the left hand side you've got 1 1 1 1 2 1, and on the right side you've got 1 1 1 1 2 1. And again, this goes down to the next layer as well. So 1 3 3 1 3 3 1 3 3 1. It's going to go back like that. Now the interesting part here is that if you have this, at some point there's actually a gap in the middle. And it should be right here, I think. Yeah, it's right here. This one's actually a 6. And the guys who looked at this said, well, if we've cut off the Pascal triangle that exists on the, let's go with cut off the one on the left. So we drive a plane straight down through, or I guess at a diagonal, depending on how you draw it, through the Pascal triangle. Then what we end up getting, or what we end up being left with, is this 1 that's here, 2 2 3 6 3, and then if we chop that one off as well, we would have left the 1 from here and the 3 3 from here, and then this would keep going on to the next layer down as well. And then lastly we'd have this 1 here, which then would go down to the next layer and keep expanding out like that. Give you a hint, the next one down here is 4 and 4. And next one down here is going to be 3. No, it's not 3 6 3. Yeah. 4 8 4. And then the one here would be 4 12 12 4 and a 1. So the pattern that exists, they found, was when you drive a plane through the first face of the Pascal triangle, then you're left with what ends up being an advancing pattern. So here you have 1 times the 1 that we had to begin with. And then on the next layer down we have 2 2, which is 2 times 1 1, which is the next layer down on the Pascal triangle. So 1 1 should be the next one. And then 1 2 1 should be the next one. But it's going to be 3 times that. So 3 6 3. And then the next one down should be 4 times that, or 4 times 1, 3, 3, 1. So 4, 12, 12, 4. And then again, as you keep cutting off faces of the Pascal's triangle, the first one was just a linear multiple, or sorry, a constant multiple of the Pascal's triangle. The next one over was an advancing common multiple, so a linear pattern. The next one ends up being quadratic. The next one ends up being cubic. And I was like, oh, that's really cool. So these patterns keep advancing further and further as we go in. I, on the other hand, in the meantime, at pretty much the same time that they were figuring this out, ended up taking the Pascal triangle here, or the tetrahedron, and cutting it instead of along its faces, I cut it horizontally, as you see here, as I grouped them here. And so I ended up with this thing. So one here. Uh-oh. Now that should have been a 6, huh? Yeah. Yeah, that should have been a 6. And that should have been a 12 as well. Well, nuts. So 6, 12, 6 going that way. All right, then 1, 4, 6, 4, 1 going back. Anyway. So what I was doing was I was looking at the individual layers of Pascal's tetrahedron, so I called it. And I explained this pattern to one of my friends, and he said, "Oh, you mean a simplex?" And I said, "I've never heard that term before." And he said, "Yeah, a simplex is the smallest shape that you can make given n dimensions. So n simplex, you end up with a 1 simplex is just a line of a certain distance, so usually just 2, I guess. It doesn't matter. The next simplex up, a 2 simplex, would be just a triangle. It's the smallest closed shape that you can make. 3 points, 1, 2, 3, you connect all of them, you make a triangle. A tetrahedron is the smallest shape that you can make in 3 dimensions. So you have a point, and then you have 3 other points which define space outside of a plane, and now you draw all those lines in. So 1, 2, 3 defines a plane, but then as soon as you put one more point in, now you've got something that is extraplanar. It has to come off the page. When you connect all of them up, it makes a tetrahedron. So this is a 3 simplex. Two simplex just being a regular triangle. 1 simplex is a line segment, or what Euclid would call a line, and technically a 0 simplex would just be a point. My pen is acting up today. Okay. So 0 simplex would just be a point. 1, 2, 3 simplex. And then technically you could have a 4 simplex as well. The problem with a 4 simplex is that you would be drawing a hypertetrahedron, which I am not particularly gifted at trying to draw. This is terrible. I'm not doing well tonight with this. Whoop. Alright, so here you would effectively draw in connections between each of the tetrahedra. And now a 4 simplex is this hypertetrahedron that goes like this, connects all these points. And then you could keep going, 5 simplex, 6 simplex, etc. Well, then I had the idea of making a visual diagram or a visual representation of the 3 simplex as a 3D printed object that you could then drop balls into. This comes from an exhibit at the Boston Museum of Science. It was called Mathematica. And in Mathematica, they had a representation of what was really a pachinko board. So the other one being proprietary, I cannot say the name, so hooray. So basically what you had was a bunch of balls that were coming out of a chute up top that came out of one single place, and they immediately were met with a peg that was stuck in the middle of this little plexiglass thing. The balls, in theory, could not escape anywhere. Sometimes they get stuck in places, but they would hit this and they would have to go either to the right or to the left, where in theory they would hit another peg that was in here, and those would either go left or right, where they would hit other pegs. And so on and so forth. You've probably all seen this before. There is a famous game on a game show running midday that has to do with prices and whether or not they are correct. So they have a proprietary version of this where you can win cash prizes and all that. The Mathematica one at the Boston Museum of Science shows you how the binomial distribution works. As we get toward the bottom, we've got slots for all of the balls to land in. And the balls will follow these kind of meandering paths that go all the way down through all of the other pegs until they get to this last row where they drop into place. And there was also a line that was pasted onto the front of it. And invariably, the pattern that was sampled by these balls being thrown through the top of this chute and then bouncing through these pegs ended up following this particular pattern pretty closely. Not 100% accurate, but some were over and some were under. But on average, they came out to be the exact number, or really, really close to these exact numbers. Every single time. So this is a binomial distribution. So if you're ever in the Boston area, go to the Museum of Science. Check out the Mathematica exhibit. It's really brilliant. They've got a whole bunch of other stuff in there too. But I was inspired by this and said, what if we were to take this and do it in 3 dimensions? We could create a 3D printed object that basically had like a bunch of circular chutes that allowed these to drop into them. And so I thought, you could pack these cylinders together. And then have the balls, which would be probably ball bearings, for instance, go through these chutes and end up in some sort of collection tank at the bottom. The collection tank at the bottom would then hopefully have a three-dimensional representation of this distribution, this binomial distribution, but it's not a binomial distribution anymore. It is now a trinomial distribution. And so we would end up with a three-dimensional curve at any given, after any given dropping of these ball bearings through the whole system, starting all the way at the top with our number 1 at the top, and then letting them fall all the way through. And what does this have to do with anything other than my channel? Well, the numbers here should represent the number of paths that you could take to get to any one of these particular numbers. So I said if this was, like this was our A direction, this is our B direction, and this is our C direction, we could, one of the other problems was how would you prevent these things from, like the balls from landing directly in the center. And so we had to like think, okay, we can fill those in with like little stoppers, sort of, that are pointed so that they have to fall off to one direction or the other. My original thought was kind of a honeycomb pattern. So this is actually what you see in my profile picture. So the N-Simplex Pachinko profile picture has this hexagonal shape that can come off of this. And any one of the chutes from the upper level would drop it exactly on, as close as we could, the center of the next layer, right on one of these cross points. If it lands right on the cross point, if it has any momentum at all, it's an unstable equilibrium. It's not going to stop there. Even if it were potentially going to stop there, we could again make it more like a knife edge. And so 3D printing, you know, you could make it a little bit sharper, and it would kind of deflect one way or the other or the other. So you've got 3 different possible ways for this to go. Once it hits this particular cross point, it is either going to fall up and to the left into this one, to the right into this one, or down and left into this one. And then those would drop through onto the next layer. And like I said, each of these individual numbers, as we keep going down, give you the number of paths that any one ball could take to get to each of these locations. So if you're all the way in the corner, there is only one possible way to get into the corner and remain in the corner the whole way. As you get into the middle, these are the ones that are more interesting. You're bouncing back and forth, or bouncing in one particular direction, but now you've got more paths to get there. So you can go a bit further to the right and then to the left and then to the right, or you can go left and then right a long way. You know, there's a lot of stuff you can do. So because this is very much like a pachinko machine, where you have this pattern where this is going to bounce through a series of like pins in here, that's why I named my channel here N-Simplex Pachinko, because now we can even do the pachinko modeling in 4 or 5 or 6 dimensions in order to get the values. How many paths would you need to get to any one of these places? Now it's a bit crazy. I have not been able to figure it like figure out how to get the numbers in Python, if anybody's watching and wants to do it, you have my permission. I'd like to be a co-author. And then probably do some sort of experimentation to prove that, after a certain large number of trials, you do get approximately these proportions. There's probably a few other things we could talk about here, but yeah, there was another good one. What did I forget? Oh, yeah, at one point I did, in fact, prove the trinomial theorem by hand and show exactly what it could be. I found this result, I got these results, and then I went online and it was just right there. I'm like, oh, guess I could have looked that up instead of spending all afternoon doodling in my notebook, but it was a good exercise. So anyway, the n-simplex model ends up being something like for n dimensions, we want p trials, and you end up with, again, something like a sub, a sub 1 plus a sub 2 plus ... all the way out to a sub n raised to the p. So an n-dimensional object that has p trials, whatever, however many layers we're trying to drop this thing through. That's what our p is in this case. All right. So if anybody is interested in doing some research in this, like I said, you have my permission, but I would like to help you out, be a co-author, anything like that. Let me know. All right, I think I am going to end the stream. So since there's nobody else here, I'm talking to myself. All right, so thank you everybody for coming last week. Had a good time. If anybody does have any more questions, feel free to drop them at nsimplexpachinko@gmail.com. It's just the same as my username. I will endeavor to get other questions, and next Wednesday I am going to look into, if nobody else comes, I will end up doing some of the pre-calculus stuff that I've kind of invented over the years. So I think we're going to start with absolute value, and maybe in subsequent streams, or possibly next week if we just happen to be happen to have time for it. I'll talk about parent functions and graphing transformations. So I have a slightly different formulation on it that I've been working with my students. And this Friday, that is the 29th of January, I'm going to be doing the more advanced tactics and strats for my run of Outer Wilds. So if anyone is interested in that, again, if you have not played Outer Wilds, it is on Game Pass. I suggest you go ahead and do that. And at any rate, I will see you all later. Good luck. Have fun.